This instructional companion on friction coefficients falls under the major topic, Dynamics and Vibrations, which contains the following 5 chapters. We've got a thunderstorm going on here. Properties of solid bodies, kinetics, which is where this particular instructional companion will come from, mechanisms and power transmission systems, and vibrating systems. The chapter on kinetics contains a great many topics, one of which is about flattened belt friction, from which this discussion on friction coefficients is going to be coming from. Well, why do we need to have a discussion on friction coefficients? Well, there's going to be 2 reasons. The first one is, and as mentioned in the MERM, is that the tables can only give relative values, the relative resistance to motion for one pair of surfaces compared to another. The exact values that you see there, the ranges and things, are almost worthless. You just can't trust them. You need to determine them yourself, and that's what the first discussion is going to be about, trying to come up with how do you determine the coefficient of static friction. Again, I use μs, as you know from the previous instructional companion on impending motion. The MERM uses Fs, F sub s, and I'll try to maintain that here. Basically, you determine it by putting a block of one material on a surface of the other material, raise it up, and when it slips, that can be related to the friction coefficient. The formula that's in the MERM is tangent phi. How I would call that tangent phi would actually be a phi would equal tangent or equal theta max, the max angle that you would use here. So what I really like to do is really to write this a different way, is that the friction coefficient that you're looking for is actually the tangent of theta max. So you can actually do this experiment. We have in actuality, and works wonderfully, and you get values that you can take to the bank, not the ones that you see in the table in the MERM or anywhere else. Okay, you just aren't going to find them. We had a problem in a job one time where we needed to know the friction coefficient of a brake pad for using as a clutch to protect the transmission. Called the company. Well, they basically hung up on us. So we took the brake pad, put it on a piece of steel, did this experiment, and came up with a value that was right on. Question is, where does this come from? This is not in the MERM. Okay, and we're going to show you that, and it's important to show that. Very, very valuable statics problem. We'll decide to let the thunderstorm pass. Well, here's the free body diagram of the problem of the block on an incline. 3 forces: weight, friction force, and the normal force. Now, I do have a issue with the way the friction force is located on the block in the MERM, as Rumsfeld, the former Secretary of Defense, would say. I have a minimum of high regard for that practice. He sort of shows the friction force as pulling on the block. Well, it isn't. It's up underneath. Now, the question folks have always with blocks and inclines and things is, which way are you going to set the coordinate system up? Well, to me, it's a vote. Okay, I got 2 forces along the incline and 1 not, so I'm going to use the inclined coordinate system. Okay, and so I'm going to make that perpendicular and this up the incline, and of course my counterclockwise. Okay, so but what we need now is to get the W organized. So let's do that. Okay, again, to save YouTube time, come over here and show my W. I kind of do this myself all the time. Bring it over here and try to do it on the diagram. And so it breaks into 2 components. If this angle is theta, that angle is theta. So this adjacent side is W cosine theta, and the opposite side is W sine theta. And the W sine theta is what is driving the block down. The friction force is opposing that. Okay, well, what do the equations of equilibrium look like? So again, to save YouTube time, what we have here, the first, some of the forces in the X, well, positive up the incline, could have made it down, because we know the impending motion, it's not motion, but the impending motion will be down. That's what the friction force is opposing. F of F minus W sine theta equals 0, equation number 1. Sum of the forces in the y, N minus W cosine theta equals 0, equation number 2. And as you see me write out in the instructional companion impending motion, I can't take moments because N's not located. So what do we do now? Well, remember, this problem is about raising the incline until there is, in fact, motion. So what you can say then, I'm going to move this up a tad here, is, and this is the way I write it out, as theta goes to theta max, okay, the friction force goes to the maximum value, and that maximum value is, and I'll try to use the symbols in the MERM, FSN. And there's our third equation. Okay? But now what we have to do is go back and substitute in, but where now theta is not just theta, it's theta max. And we'll do that on the next page. Okay, from equation 2, we've got N equal W cosine theta. Now in the MERM, he goes on and puts it as mg cosine theta. Well, that's okay. However, in the US system, you're almost assuredly going to be given W in pounds, whereas if it's an SI problem, you may very well be given mass in kilograms. So both of those are valid, but I'm going to stay with the W cosine theta. And so now the friction force is the maximum value, but it's now the friction force Fs, or the friction coefficient Fs, W cosine theta max. The normal force still stays the same no matter what the magnitude of theta is, but you can't make the assumption to mu s or Fsn without that being a maximum value. So then equation 1 becomes, instead of just being f of f, it's now f of f max minus w times sine theta max, not just theta, sine theta max. So if we substitute this for f of f max, we end up with fsw cosine theta max minus w sine theta max. And what's not shown in the MERM, none of this is shown there, but what happens is the w's cancel, and so what you're left with, if we rearrange this algebraically, we end up with fs, comes out to be sine theta max over cosine theta max, which of course is equal to tangent theta max, and that's what we've been after. Okay, the fact is, the result is you can find this coefficient of static friction by doing this particular experiment, measuring the angle and then taking the tangent, and you have a really good number, believe me. Okay? Well, what about the other coefficient of friction, the kinetic? Okay, the determination of the kinetic coefficient of friction is not done in the MERM at all. The way that's done is you take a block, and I've made it so that it doesn't tip over. I have added I mean, you could have something more accurate, but just to talk here, a fish scale. Get the spell right here. A fish scale. And what you're going to do is pull on this block, and as you're pulling it and sliding along on that constant line, if you remember, you're going to register that particular P sliding, and then from there you will be able to determine. Well, how do we do that? Well, we'll do it with a free body diagram that we're moving. Okay, again, to save YouTube time, here's the free body diagram with the four forces acting on it. But in this case, the block is sliding along at a constant velocity. Very important here when we get ready to do our equation. Constant velocity, and you're reading that number, and we know what that is. Well, let's look at the equations. Okay, well, if we use our standard system, x, y, we won't need a moment here. Well, some of the forces in x equal ma, but a is equal to 0. Okay, a equals 0 because we have constant velocity. So we have the force P to the right, friction force back to the left equals 0. And of course, in the vertical direction, we've got N minus W equals 0. And our friction force here, we could write it down, but the friction force with sliding is just our F sub K times N, and here N is equal to W. Okay. So let's pull all that together on the next page. Okay, from equation number 1, again we had P sliding, which we know what that is because we're looking on the fish scale as we're pulling this along at a constant velocity, minus f of f, and as we said, f of f is equal to fk in, and in this particular problem, that's w, the problem we're doing here, this experiment, n is equal to w. So now if you solve for f sub k, well, it's just as equal to the P sliding over w, the weight that you know. How about that? Really nice experiment. Easy to do. Okay, very easy to do. So again, what we're getting, this is from the scale, whatever you want to use. I say I've used a fish scale to kind of use that for visualization, but actually that would be a very good thing to use. Just use an accurate one. Give you a really nice number. Remember the other one, to summarize what we've got here, we remember Fs, our coefficient of static friction, is found from the block on the incline, tangent, theta, max. And I would keep both of those somewhere, not only for work, but believe me, this is a great science project. When your child at 10 o'clock on a Sunday night says, I need a science project the next day, this is it. You can go into the closet, you notice the area doesn't matter, the weight doesn't matter, get all kind of shoes out of the closet, big shoes, dad's shoes, mom's shoes, all those kind of things, find different surfaces, concrete block, pieces of wood, and get your little adjustable triangle out, and away you go. I've done that 3 times, actually. I have 3 kids, and I've done that one 3 times. I get out there with my little measuring triangle. Okay. In fact, I couldn't resist to go find it here. I've had this from a long time from my drafting days. Adjustable triangle here. Measure those angles, and away you go. I know it's probably an antique. Probably could get a lot of money on eBay for that. Okay. So now you know how to find those values. You don't have to look them up in a table. You can do these very accurately. The more accurately you do, the more accurate your number. Okay? Again, I invite you to visit my website as part of your exam preparations and plan of study.